All right, buckle up, everybody, because we're about to dive deep, and I mean deep, into the world of quantum technology. But get this, we're going way back to the 19th century to trace its roots.
That's right. We're talking about a time before quantum mechanics was even a glimmer in anyone's eye.
And yet, the work of one brilliant physicist, James Clerk Maxwell, laid the groundwork for some of the most mind-blowing tech we have today. Quantum computers, cryptography, the whole shebang.
It's amazing to think how a scientist working over a century ago could have such a profound impact on the future.
Absolutely. And to guide us on this incredible journey, we're turning to an essay by Yorgo Schneeppat titled James Clerk Maxwell, Electromagnetism and Quantum Technology. This essay, well, it's packed with insights into Maxwell's life and his lasting legacy. And trust me, this isn't just some dry history lesson. It's about understanding how the very foundations of modern technology, the technology that's shaping our world right now, are built upon the work of a true visionary.
Schneeppat really brings Maxwell to life, starting with his childhood. It's like this kid was practically born a physicist.
I mean, I read that he published his first scientific paper at 16. 16. I was probably trying to figure out what to wear to prom at that age.
Right. And here's Maxwell tackling complex scientific problems.
So what was he working on? I mean, what kind of science can a teenager even grasp, let alone publish on?
Well, Schneeppat talks about how, even as a young boy, Maxwell had this insatiable curiosity about the world around him. He was fascinated by everything from light and color to the geometry of soap bubbles.
Okay, so we're not talking about your average childhood experiments with baking soda volcanoes here.
No, this was something special. It's clear that Maxwell had a natural talent for math and a deep-seated passion for understanding how things worked.
And that passion obviously led him to a place like Trinity College, Cambridge.
Exactly. Schneeppat really emphasizes the importance of this environment in shaping Maxwell's thinking. Trinity College in the mid-1800s was like a hotbed of scientific thought. It was the place to be if you were a brilliant mind wanting to push the boundaries of knowledge.
So he was surrounded by other brilliant minds, all pushing each other to be better, to think bigger.
Absolutely. Schneeppat points out that this is where Maxwell really honed his mathematical skills, which, as you know, are essential for any physicist.
Yeah, I can't imagine trying to unravel the mysteries of the universe without a solid grasp of math.
Well, you and Maxwell have that in common. He had this amazing ability to translate complex physical phenomena into elegant mathematical equations.
And it was this ability that led him to make one of the most groundbreaking discoveries in the history of science. I'm talking about his work on electricity and magnetism.
Ah, yes. This is where Maxwell's story takes a truly electrifying turn.
Pun intended.
Maybe.
But seriously, at the time, electricity and magnetism were seen as these separate, almost mysterious forces.
And then along comes Michael Faraday. He was doing groundbreaking experimental work with these forces, but he didn't have the mathematical tools to fully explain what he was seeing.
So Faraday was the artist, experimenting with colors and textures, and Maxwell was the master weaver, creating the grand design.
That's a great way to put it. Schneeppat highlights how Maxwell took Faraday's experimental observations and transformed them into a set of equations that would forever change our understanding of the universe.
Those famous Maxwell's equations, right? They're practically legendary in the world of physics. But I'll admit, I've always been a bit intimidated by them. All those symbols and mathematical jargon.
I understand. They can seem daunting at first glance.
So can you break it down for us? What exactly do Maxwell's equations do? I mean, I know they're important, but I'm not quite sure I grasp the full significance.
Well, imagine this. Before Maxwell, electricity and magnetism were like two separate islands in the vast ocean of scientific knowledge. What Maxwell did was to build a bridge between those islands, showing that they were actually part of the same continent, two aspects of a single fundamental force, electromagnetism.
So he didn't just describe these forces, he unified them.
Exactly. And the implications of this unification were profound.
I'm guessing this is where light comes in, right?
Mhm.
Because light is an electromagnetic wave.
Yes. Light is an electromagnetic wave, and Maxwell's equations predicted its existence before it was even experimentally confirmed.
Wait, so you're telling me that light is just that electromagnetism in action?
Precisely. It's like this hidden language of the universe, and Maxwell cracked the code.
Wow, this is incredible. I mean, it's hard to overstate the significance of this discovery. It's the foundation of everything from radio waves to X-rays. It's the reason we can communicate wirelessly, see inside the human body, and explore the depths of space.
It's also why we're able to have this conversation right now through the magic of microphones and radio waves.
That's all thanks to Maxwell. But now I'm curious about something else I read in Schneppat's essay. He also talks about Maxwell's work on the statistical behavior of gas molecules. Now, that seemed like a bit of a detour to me. How does that fit into the story of electromagnetism and quantum technology?
That's a great question. And it's one that Schneppat addresses head on. He argues that Maxwell's work on gases, what we now call statistical mechanics, was incredibly important for the development of quantum theory.
Okay, I'm intrigued. But how does studying the behavior of gas molecules relate to the quantum world?
Well, think about it. Maxwell was exploring how these tiny particles, the molecules, move and interact in a seemingly random way. He was using probability and statistics to describe their behavior.
Okay, I'm starting to see a connection here. The randomness of those gas molecules.
Yeah.
Is that kind of like the uncertainty we see in the quantum world?
Exactly. Maxwell's statistical approach laid the groundwork for understanding concepts like probability distributions, which would later become essential for describing quantum states.
So it's like he was unknowingly planting the seeds for a scientific revolution that would blossom decades later.
It's almost like he built this incredible foundation but didn't quite realize what kind of structure could be built on top of it.
That's fascinating. And a little bit mind-boggling, to be honest.
But that's the beauty of science, isn't it? It's full of unexpected connections and surprising twists and turns.
I'm definitely ready for the next twist. So let's delve deeper into the quantum realm and see how Maxwell's work, even with its limitations, paved the way for the mind-blowing technologies we have today.
Let's do it. All right, so where were we? Yes, teetering on the edge of the quantum abyss.
I'm still reeling from the fact that Maxwell's work with gas molecules somehow connects to all this.
It's incredible, isn't it? But before we get ahead of ourselves, remember that cliffhanger from last time?
Oh, right. You mentioned this black body radiation problem.
A problem that nearly brought classical physics to its knees.
Okay, now you have to explain.
All right, all right. Imagine an object so dark, so mysterious, that it absorbs every single bit of light that hits it.
Like a cosmic vacuum cleaner for light.
Exactly. No reflections, nothing. That's why it's called a black body.
Okay, I'm picturing it, but why is this a problem?
Well, it turns out, even though it absorbs everything, a black body also emits radiation.
That's kind of weird, isn't it? Like, it's this void, but it's also glowing?
Well, everything emits radiation. Even we do. Though I doubt we're as exciting as a black body.
Good point.
The thing is, the type of radiation a black body emits depends only on its temperature.
Okay, so the hotter it is, the more intense the radiation. Makes sense.
But here's where classical physics goes off the rails. According to Maxwell's equations and everything else we thought we knew, the intensity of this black body radiation should just keep increasing infinitely at higher frequencies.
So basically, the hotter it gets, the more it should blast out an insane amount of high-energy radiation.
Exactly. It's like the universe should be flooded with this crazy cosmic microwave oven energy, a real ultraviolet catastrophe, as they called it.
Yeah, I'm pretty sure I wouldn't want to be around for that.
And thankfully we're not, because what we actually observed doesn't match up with these predictions at all.
So there was a huge disconnect between theory and reality.
A massive one, and it sent shockwaves through the world of physics.
So what do? Just ignore it and hope it went away?
Haha. I wish. No, this was a crisis. It meant that something was fundamentally wrong with our understanding of how light and matter interact.
Enter the quantum revolution, right?
Precisely. And Schneppat really emphasizes this point. It was this very crisis that cracked open the door for quantum mechanics.
So who was the brave soul who stepped up to solve this ultraviolet catastrophe?
Well, it was a physicist named Max Planck, and Schneppat describes him as a reluctant revolutionary. He was deeply committed to classical physics, but even he couldn't ignore this glaring problem.
So what did he do? What was his big idea?
In a moment of sheer brilliance, Planck proposed that the energy of electromagnetic radiation, like light, wasn't continuous as Maxwell's equations suggested. Instead, he said it was quantized.
Quantize.
It means that energy can only exist in discrete packets, like tiny bundles of energy.
Hold on, so instead of this smooth flow of energy, it's like it comes in little chunks.
Exactly. And each chunk, or quantum, has a specific amount of energy.
That seems so counterintuitive.
It goes against everything classical physics had taught us, but it was the key to solving the black body radiation mystery.
Okay, I'm all ears. How did it work?
Planck said that the energy of each quantum is directly proportional to the frequency of the radiation.
So higher frequency means higher energy per quantum.
Precisely, which means that at those really high frequencies, It takes a lot of energy to emit even a single quantum.
So it's like there's this energy barrier preventing the black body from going crazy with high-frequency radiation.
You got it. It's like a cosmic speed limit for energy.
That's incredible. So by introducing this idea of quantized energy, Planck managed to perfectly explain the black body radiation spectrum and resolve the ultraviolet catastrophe.
He saved the universe from a meltdown, one quantum at a time.
And to think, this all stemmed from trying to understand how a perfectly dark object could glow.
And Schneeppat reminds us that Planck's breakthrough, as revolutionary as it was built upon the foundation laid by Maxwell.
It's amazing to think that even when Maxwell's equations fell short, they still pointed the way forward.
It's a testament to the interconnectedness of science, how even limitations can spark new discoveries.
So even though Maxwell couldn't have foreseen the quantum revolution, his work was a crucial part of the journey that led to it.
A journey that's still unfolding. And in our next part, we'll explore how Maxwell's legacy continues to shape the cutting-edge world of quantum technology.
Welcome back, listeners, for the grand finale of our James Clerk Maxwell adventure.
We've seen how his work unified electricity and magnetism, predicted those electromagnetic waves, light, and even laid the groundwork for, get this, quantum mechanics.
Mind-blowing stuff, but as Jurgo Schneeppat reminds us, this isn't just ancient history.
Nope, not at all.
Maxwell's equations are still shaping our world in ways he could never have imagined.
Powering some of the most mind-boggling technology we have today.
Quantum computers, cryptography, sensors that can detect things on an atomic level.
It's like, how is that even possible? Equations from the 1800s driving the future.
Right. It's like building a spaceship with instructions from Leonardo da Vinci.
A bit of a head-scratcher, but Schneeppat makes a compelling case. Maxwell's work is deeply intertwined with quantum technology.
So how does that work? I mean, how do you go from describing electricity and magnetism to building a quantum computer?
Well, let's start with the heart of a quantum computer, the qubit. The quantum bit of information.
Right. Unlike a regular bit, which is either 0 or 1.
A qubit can be in this weird state called superposition.
Both 0 and 1 at the same time.
It's like that coin spinning in the air, both heads and tails until it lands.
Yeah, I remember that analogy.
Now, to build a quantum computer, you got to be able to control these qubits, manipulate their quantum states with incredible precision.
Sounds tricky.
And guess what plays a starring role?
Let me guess. Electromagnetic fields.
Bingo! Schneeppat explains how we can actually nudge these qubits into specific states using carefully controlled electromagnetic fields.
Kind of like herding quantum cats.
Huh.
In a way.
But how do we control those fields so precisely? Well, that's where Maxwell comes in. His equations give us the blueprint for understanding and controlling those electromagnetic fields.
It's like he handed us the instruction manual for talking to these quantum particles.
Exactly.
And without that manual, well, we'd be stuck.
No quantum computers.
No way to harness the power of these qubits to, revolutionize everything from medicine to material science.
It's really remarkable.
Okay, but what about quantum cryptography? I know it uses photons, tiny packets of light, to transmit information securely.
And that, my friend, also ties back to Maxwell.
I had a feeling you were going to say that.
Quantum cryptography relies on these mind-bending quantum principles like superposition and entanglement.
The spooky action at a distance that Einstein was so puzzled by.
Exactly, but the way those photons behave, how they travel, interact, get manipulated.
That's all governed by Maxwell's equations.
The foundations of electromagnetism at work in the quantum realm.
Maxwell's legacy strikes again.
It's everywhere.
Speaking of everywhere, what about those quantum sensors you mentioned? The ones that can detect stuff at the atomic level.
Ah, yes, those are incredible.
How do they even work? And what could you use them for?
Well, imagine sensors so sensitive they can pick up the tiniest changes in magnetic or electric fields.
Okay, I'm imagining.
Think medical imaging, where you could detect tiny tumors, monitor brain activity in unprecedented detail.
Wow.
Or super accurate navigation systems that use the Earth's magnetic field.
All thanks to quantum sensors.
And at the heart of those sensors, you guessed it, our understanding of electromagnetism, courtesy of James Clerk Maxwell.
So we're using the same equations that describe lightning to probe the inner workings of atoms. That's wild.
That's the power of fundamental physics.
It's like discovering a universal language that allows us. So, to all our listeners out there, keep exploring, keep questioning, keep pushing the boundaries of knowledge. And who knows, maybe you'll be the one to make the next great leap forward, inspired by the enduring legacy of James Clerk Maxwell